Hi, everyone. I'm Joe. I'm at MIT. Today, I'm going to tell you about how we reverse engineered some smartphone optical assemblies that are in all of your pockets to develop new miniature microscopes for neuroscience that we can use to image in very small animals like this zebrafinch songbird on the right that we study in the lab. And this is all work that was done by these wonderful people in Michael Fee's lab. So over the past decade or two, neuroscientists have become increasingly obsessed over recording as many neurons as humanly possible in an animal while it's performing a behavior. And there's two main schools of thought for how to do this. One is to build an enormously complicated device like you see on the left that can record a bunch of neurons in an animal with its head fixed. The other is to build a tiny implant that you can mount on the head of an animal while it is freely behaving and performing some kind of task that you want. So I'm going to tell you about an approach that we took using the second tiny implant strategy. So this is the device. It weighs 1.4 grams. I have one in my pocket if you want to check it out later. But to give you a sense of how it performs, the field of view of this microscope is an improvement over existing technology by an order of magnitude while still being able to resolve single cells. So it has a resolution of about 2 microns, which is important if you want to record the activity of individual cells within a circuit. So this is what the data actually looks like. So we're observing thousands of neurons, over 2,000 neurons inside the brain of a mouse in mouse cortex while the mouse is freely exploring a circular maze. And so you can see in the inset here, we can resolve individual cells as these bright spots. So I spent a lot of time just staring at these beautiful videos. It's a great job. So I want to give you some intuition for how this system actually works. And sort of the big picture question here is, why are high-performance optical assemblies so complicated and expensive? If you get a new camera lens for a fancy camera, why is it so expensive and why is it so heavy? So the main issue, I think there's a slide missing. But so an ideal lens is, what you want an ideal lens to do in an optical system is to focus a bunch of light that is coming in parallel into a single well-confined point. And that's going to give you a nice crisp image if you're trying to use it to image a scene. But in reality, what happens if you try to use a single lens that has a spherical surface, you get all sorts of what are called aberrations, where the light rays are not actually focused to a point, but rather, depending on where the light hits the lens, it gets focused to a different point. And then if light is coming in off-axis at an angle, you start encountering other problems as well. There's something called coma, astigmatism. It gets very complicated very quickly. But the intuition here is that single spherical surface optical elements don't perform nearly as well as you need them to in order to do high-performance imaging. And there are two main ways to get around this. One is to make a lens that has an aspheric surface, say described by some polynomial, and that allows you to improve on performance metrics like the spherical aberration. The other is to chain a bunch of optical elements together into an assembly that is extremely complicated and expensive. This assembly is from a photolithography setup. These things cost enormous amounts of money. And so what we did instead is we took advantage of essentially hundreds of millions of dollars of research and development that has gone into developing these very high-performance plastic aspheric lens assemblies that are probably in all of your pockets. And so we could just yank one of these out of a smartphone. This one I cut in half and stuck under a microscope. You see it has 7 different optical elements, all of which are highly aspheric. Some of these surfaces are described by up to 12th order polynomials. And this is something that you can buy wholesale for a couple dollars, which a couple decades ago was almost unthinkable. And so the way that we use these to build a microscope is we borrow a trick from photography called the double macro lens configuration, where you take one lens and you orient it sort of as you would in order to take a picture of a landscape, say, where it's taking light that's coming in collimated and focusing it to a well-confined tight point on an image sensor. You take another lens assembly and you flip it backwards and put it over the first one. And what this does is it relays all of the light from a single point in the brain to a single well-confined point on the image sensor. And so what this acts as is a one-to-one relay imaging system where the pattern that is in the brain gets projected onto the image sensor. And using this approach, you can get very large fields of view with very high optical performance, almost for free. And so using that neural activity that I showed you in that video earlier, we are able to decode the position of the mouse in this maze while it was exploring using only the neural activity with over 3 times chance level, which is an example of the kind of sort of neuroscience that you can do when you can record from very large populations like this. And my time is up.
So I assume your depth of field is not super big. Can you like tune that around live so you can look deeper and shallower into a brain?
Yeah, good question. So this is a single photon imaging regime where you're limited pretty strongly by in terms of how deep you can go in the tissue because of scattering. So we're really only looking at the top surface.
This is cortical.
Yeah, that's right. Yeah.
Since you have this one-to-one map, can you also use this to sort of map light onto the same substrate as you're doing the imaging to target things?
Yeah, that's a very good question. So people have developed systems to do that. In our particular instantiation, the way we have it set up, it's not particularly easy to do that, but that's definitely a possibility. People use these very small spatial light modulators from portable projectors to do exactly that.